Okay, so today we'll start three-phase system, or we call it polyphase because sometimes we can have more than three phase. So before we discuss about this, let us go through the part why do we go for three-phase system. Okay, so say you have a generator which is single phase. We assume it to be single phase generator. So hello,
Yes, sir.
am I connected to
Yes,
you?
sir. Yes, sir. Yes, sir.
Okay, because there is a warning coming which is saying that there's a connectivity issue. Anyway, this is your impedance Z, and you
I
have
think your screen is frozen.
now. I'm
Sir,
writing on
for me,
screen.
I am restarting.
Okay, anyone else? Can you see how I am changing the diagram? Can you see it?
Yes,
Yes,
sir.
sir.
Okay. Okay, then maybe for you it is frozen. Okay.
Yes, sir. Now it's good.
Okay.
Yeah.
Okay. Okay. So you have the three different sources E1, another is E2, and for that it is say it is Z1, Z2, and there is one more. This is Z3. Okay. So now if our E1 equal to E2 equal to E3, huh? I don't know. Again, that same problem has come back. It is like one horizontal line is coming. Anyway, E1 equal to E2 equal to E3. If the sum of these three is equal, if the magnitude of this all these three voltages is E, and if they're placed at 120-degree apart, then we can how this we can develop that I'm coming later. But before that, let us assume that E1, E2, E3 having the same magnitude. The magnitude is same, which is E, huh? And they are 120-degree apart from one another in phase from one another. Then what we can do, we can join this two line, again this two line, and then remove this. Oh, sorry. So if we redraw it, it will look like this. And one with one line we replace this connection. Earlier there was total six conductor, six were starting from each source. There was, this is one, there was another for returning, so it was three phase circuit, six were. But now we can see that if we just connect them in one side and join them with another wire, then it will change to three phase four wire system, four wire. So why do we go for this? Why do we go for three-phase four-wire system? Because whenever we are using six-wire, we are delivering the same power, but unnecessarily we are taking more number of conductor. That means it was costly, right? We can save the conductors if we go for a three-phase four-wire system, and later we'll see that if we go for a balanced load, like if Z1 equal to Z2 equal to Z3 in terms of magnitude and phase. I mean, your same RL load or same RLC load, all the power factors are same and their impedance value is also same. Then we can replace this fourth wire also, because sum of this all three currents will be zero when it is a balanced load. So then for the three phase circuit, we can have a three phase three wire system. Three phase three wire system. Okay. But if these loads are not balanced, like if Z1 not equal to Z2 not equal to Z3, then we should keep this line, this neutral line, with which the sum of these three current at this particular node will be non-zero. So we have to keep this, otherwise the neutral point will shift. Okay, so whenever we develop polyphase or three phase supply, we should have a alternator like this. This is your uh, stator, which is having the armature coil. This is the stator, and this is your rotor. And you place a coil here, A dash, in the armature circuit. This is your electromagnet or maybe permanent magnet. Usually it is electromagnet when we go for the parts in the generating plant. When we take alternator here, this will be electromagnet. This is your stator, and here you have another coil, B dash, and C dash. So what happens when the coil for when the coil at A at a certain point, you will be having your maximum field strength. So with the flux line will cut maximum link with A dash coil. So that time it will develop a waveform like this. This is your E cell. Okay, so let us revise the drawing, and let me draw once again. So you have, this is your armature for the alternator, and this is your field circuit. Okay, this is your A dash, A dash. Now here you place B, it is B dash. So B dash, and here you place C, that is C dash. So at certain point, when if we place them at mechanical angle of uh, 120 degree, and this is also 120 degree, then what will happen after the coil, after the electromagnet comes from here to there with a, if it is rotating with a certain angular speed, then after time t it will reach at this point. So that time again your phase B will have a maximum output, right? So this is for a ea. Then after 120 degree angle, so this is 90, somewhere here, it will have its zero crossing. So it will be good if I draw in a different color, because we put this phase as red, we call it blue, and then call it yellow, or the other way around, we can call this as y and we can write as b here, we can write y here. So RYB, this is the most common form, RYB sequence, red, yellow, blue. So what will happen to the to your what should I say, your waveform? If we have this, this is your omega t, and this is your volt. So If we draw the red phase first, we'll draw it in red. So this is the waveform for red. And then what will happen after 120 degree, there will be the peak of B. I mean peak for coil B dash. That means yellow phase. So we can draw it in yellow. So this will have, this is 90. So from here this is 90. Then this is another 90. So one third of that. Sometime here the yellow phase will have its peak. Okay. Then again, uh, when yellow phase have its peak, then after 120 degree, the blue phase will have its peak, right? So somewhere this is 90. So somewhere here you will have your, so it will look like this. So red by B, and between these peaks, you will have 120 degree angle. This is 120 degree. From here to blue, red to blue, this is 240. Okay. So if you take your red phase to be a reference phasor, if red is your reference phasor, this is all the magnitude will be, Emax will be same because the same number of turn we are using, and we are placing together at this a dash. In within this a dash, if we can keep on winding more number of turns, say higher the number of turn, higher will be your induced EMF. So that we keep same for b dash and the c dash set of coil. We call them phase band actually. So this is how it is developed, and these are 120 degree angle apart when electrical angle is same as mechanical angle. That means your number of pole is same, but if we have the number of pole more here, like this is a one pole pair, if you use two pole pair, then of course this 120 degree will be divided, will be changed to 60. Why? Because theta mechanical by theta electrical will be P by 2. Or sorry, it's the other way around, 2 by P. Okay, so theta mechanical will be 2 by P into electrical, so it will be 60 degree. And then if you go for the 6 pole, then it is one third of 120, so it will be 40 degree. So you have to space your A dash in that way so that you can get all those things. So this is the relation. Accordingly, when you have the one pole pair, then your theta electrical will be same as theta mechanical, so we can place 120 degree angle apart in the armature circuit. So now if we have to draw the phasor diagram, if we take the red phase as our reference, then we can always draw the Y phase, which is 120 degree angle, and that is lagging or leading. We should take lagging, na? So because it is taking 120 degree more phase to reach its peak. So we should draw it in the other side, not this side. So we'll draw the yellow, which is, this is 90 lagging. So somewhere here 120 lagging. And we should draw the blue phase, which is 120 lagging from yellow. So you will get somewhere here. Okay. So this is minus 240, or you can write it is as plus 120, and this is minus 120 degree. Okay. So this is how you can draw your phasor diagram when you generate. So as we were discussing that we can go to from single phase to three phase, because it is taking what are the advantage of three phase circuit. Of Advantages. Conductor require, that means your copper cost is less. You can use it for the distribution purpose because you have the two sets of voltage. We'll show it later that because of the phase voltage and line voltage are available, so we can use both single phase and three phase load if we have a three phase four wire system distribution system. Then your efficiency of the alternator is high. That means your losses are less if you go for, instead of having three alternators, if we go for a three phase alternator, then efficiency is high, cost is less. Huh? And then what else? As I told that your losses of transmission is also less. Losses for transmission is less to deliver same power, and useful as many equipments are three phase. Okay, like induction, three phase induction motor, which are self starting, and construction point of view they are economical. And then if we go for the three phase circuit, then this transformer, three phase transformers are also economical to use. So because of all this we go for the three phase circuit. Okay, three phase distribution system. So when we go for the three phase distribution, I think you have the these things now. So it's a, we will discuss two things. One is your balanced.
Sir, can you show the previous slide once?
I'll share this anyway. You'll get it. I
Okay, sir.
better I'll write it in the form of slide and then share. Then it will be useful for you. Okay.
Okay, sir.
Okay. So we'll go for the balanced three phase circuit and unbalanced both. So first we'll go for the balanced three-phase circuit. So balanced Y-connected voltage source. Y-connected, or we can say star connected. We can call it star connected. So when your alternators are connected in star like this. So your EA, EB, these are in star connected, and you are using balance same impedance in for all this phase, so you will get a balanced distribution system. So balanced phase voltage are equal in magnitude and they are out of phase with another by 120 degree, and the voltage phase voltage sum up to be zero. So if you take the resultant of these three, so it will be zero. If you then that means at this point you get the zero potential. So you have two possible combination. One is if your uh, uh, I mean your electromagnet or the rotor is rotating counterclockwise with an omega with a angular frequency omega, then you can have first your A phase, then C phase, B phase, or you can have first B phase and C phase as per the construction of, as per the construction. Or if you change the polarity, then that also will change your occurrence. I mean, like the peaks are occurring, no? Like first for A, then for C, then for B. So if you just change the polarity, then what will happen here? You will get the other way around. Okay. So then your this thing will be uh, there, and this will be here. So accordingly, it will change. So these are your two possible combination as it is told, and as per their occurrence, like your peaks are achieving for phase A and then C, then B, then we call ABC, or like this way ABC, and it is ACB. So it's the other way around. Here, as per the rotation, if we go rotation wise, this will be ABC. It is written wrong, and it will be ACB. So first peak is for A, then for C, then for B, like that. Okay. So now balanced line voltages are equal in magnitude, are out of phase with another by 120 degree. That is also uh, 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 true, and we can show it. Line voltage sum up to be 0, that is also sure, and the magnitude of the line voltage is root 3 times the magnitude of the phase voltage. Line voltage lead their corresponding phase voltage by 30 degrees. So how can we get line voltage? This is how we get the three phase voltages A, C, B, or A, B, A, C, B, like this. Then if we have to find out the line to line voltage like this way, this is your VB, VA, this is VC, say. So this is VAN, VBN, this is neutral point. Cn, at neutral point potential equal to 0. Now if you want to find out VAB, so you can write it as VNAN minus VBN, isn't it? So then what will happen if you find out the phasor sum? This is the this is your phasor diagram. VAN, VCN, VBN. This is 120 degree apart, this is 120 degree. So whenever you take the minus of VBN, these are phasor quantity. So you should take the phasor sum of these two. So A, then minus of VBN is equal to VNB. So this is this side, and this angle is equal to 60 degree. So then you can find out your VAB as VAN plus VNB. So VAN is equal to VNB magnitude wise, but in between they have a phase angle which is equal to 60, right? So if they are same, then this is 30, this is also 30. That is well understood, because if this is same, this is a parallelogram, or it is a rhombus, so that means this angle will be 120 degree. This is 30, this is also 30. So you can get VAB is equal to, add, if you take the phasor sum, it is VNB cos 30 plus VAN cos 30. This is along VAB, and then perpendicular will be equal and opposite. So they are sine 30, sine 30. So VNB and VN, they are magnitude wise same. So we can write V into cos 30 is root 3 by 2 plus V into root 3 by 2. So you get V root 3, where V is your phase voltage. Okay, so this is how you can solve, or you can use the concept of your parallelogram law. So it is Vn square plus Vnb square plus 2 Van into Vnb cos of 60 degree. So if you do that, then it will be 3. If you put the magnitude wise, then you will get all those things, and this angle is 30 degree. So all these things you should remember when we go for the star connection. So for the star connected system, for a star connected system, like I can show it here, you have a star connected system. say this is connected like this, and this is your neutral line. So when there is an unbalanced load, we should connect this neutral line. Otherwise, there is no need to put this neutral line. So for the star connected system, if you have V phase voltage, then between A and B, we can write it as VL. It is line to line voltage, which is equal to root 3 into V phase. Okay. So this is true for the star connected system. So your line to line voltage, or line voltage we can call it, line V line is equal to root 3 time into V phase. Okay, I hope it is clear to you how we get V phase into root 3 is equal to V line. As if we draw the phasor diagram, then we get this. Okay, so that is okay. And then what is your I phase? This is your I phase, and that is same as IL, because the same current is flowing through this. And as you, if you use the same I mean, if you take Z1 equal to Z2 equal to Z3, same balanced load star connected, then your it will be IL for all these three lines. So I phase is equal to IL, you can write. Okay, so what is the total power consumption? Power consumption is equal to 3 into V phase into I phase into cos phi. If you are using a load like if Z1 is equal to Z2 equal to Z3 is equal to Z angle phi, then cos phi will be the power factor that you have to take care. And then here you can always write in terms of VL IL. So that will be what? 3 into VL by root 3 into IL cos phi. So you can write root 3 VL IL cos phi. So that is the total power consumption for the balanced three phase system. Okay.
Sir, what is N here?
N is your neutral line. This is your neutral line. When Z1 not equal to Z2, then what will happen at this node? What happens? This is your phasor sum of all this line current. So if they are unequal, then we'll get different line current, IL1, L2, L3. So sum of these three won't be equal to 0. Then we should put another line with which the line current can pass. Otherwise, it won't, your neutral point here will be getting shifted. So it will not be in the zero potential. Actually, when it is balanced, then this point should be 0, as we can see from here. So if you take phasor sum of this, like here we got, so sum of these two will be equal and opposite to the other, so total will be 0. But whenever these currents are different, then the neutral point won't be zero potential, it will be shifted. So to balance that, we should take this neutral current, neutral line. So this is actually three phase 4 wire system, which we'll
Sir,
discuss later.
neutral line helps the unequal current line equal to zero.
No, it will not be equal to 0. It will pass through here, but the potential has to maintain here to be 0. Okay. So if we do not do that, then your potential will change and it will look like it will no longer be a balanced three phase like this. There will be a polarity like this. So if there is a neutral drop across the source, then your for some phases it will be higher, and some phases the phase voltage will be different. So it will, from the supply point of view, it won't be distributed, equally distributed. That means it will have V phase 1, V phase 2, V phase 3. So they are unequal. Okay. So say you have designed, you are using a, I mean, for our household distribution system, we are taking delta star. So what happens, for the industrial purpose we take line to line voltage three phase supply, but for the our household supply we take single phase. And for the single phase system, we know that it is, for our system it is 230 volt. So if we do not use this neutral wire, then this neutral point will get shifted. So you can see that instead of getting 230 volt, 230 volt, we are getting more than that. So what happened then, whatever the standard or equipments will burnt out, isn't it? If you go for a higher voltage, instead of 230, if you apply 250 to certain your incandescent lamp, say for the simplest case, it will blow out, isn't it? So which is never recommended. That's why we should ground the neutral point. So neutral point will be grounded so that it is always equipotential, and this is how we get a three-phase four-wire system. Okay, so
So
if
that
we
means neutral points balance the potential difference.
here because of this fourth wire, this point will be in the zero potential, and you get the same phase voltage for each and every phase from the supply point of view. Okay, because we don't know na, for one house there will be one more load demand, and that is also variable. For another house there is a different load demand. So you are using, say you are supplying your three house using from three sources, three phases, then if there will be, I mean, high possibility for the unbalanced load. So then we should always use the neutral. So you will be seeing na, for your in your distribution box of your house, there will be always a neutral line. So one is the phase from the supply, and there will be another neutral. Okay, so that is for the neutral of this phase and neutral for the star connected distribution part. Okay, so actually these things are coming from the distribution transformer for the load distribution. Okay. So
Okay,
this
sir.
part we'll discuss in detail when we'll study the unbalanced load. But now we are assuming that we are using balanced load, and we are not taking care of this fourth wire. So neutral point, we can take three phase three wire system if we are taking Z1 equal to Z2 equal to Z3, which is Z angle phi. Okay. So this is a balanced three phase load in star connection, and this is a again it is shown with a YY connection. So if we take the balance load, then what will happen for each case, your, if this is your three different phase voltage, then this is V phase, and this is I phase. So that remains same angle, theta or phi, whatever it is. Then sum of this current will be always zero, as we can see from here. So if this same value currents are 120-degree apart, IL, 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 and then of course it will have the total current which IN to be equal to zero, right? So this is the case for the balanced Y-Y connection. That's why we can remove this line. It's not required. But if it is unbalanced, then we definitely have to keep it as I have discussed. And then for each phase, we can draw it like this. Okay. So now let us come to, there is a problem which I don't want to discuss right now. Balanced Y delta connection. This is also not required now. Okay, delta, it is not discussed. Let me discuss that. What happens for the
Sir,
delta? Yes.
sir, how can we know that the circuit are balanced or not?
Balanced means whenever you are taking same loads for the same all three phases, then we can say this is balanced. If not,
So,
then they are unbalanced. If
so
Z1
magnitude
equal
and same or all the phase and magnitude both are same.
both phase means your impedance, magnitude, and phase power factor, everything has to be same.
Oh, okay, sir.
Okay.
So potential can be different.
How come if your Z and theta is same, then for each phase you are drawing same current, then drop across that each impedance will be same, I into Z. If Z remains the same, then your IZ will remain same, isn't it?
Okay, sir. Yes, sir.
Okay, now let us draw the case when we have the delta connection. So during delta, what we have seen, that is for the star connection. Let us now do it for the delta connection. Sorry, this is EP. So we can connect like this. These are the same impedance balanced load we are taking. So this is also example of three-phase three-wire system. Okay, this is your balanced three-phase three-wire system, and the loads are delta connected. The source is also delta connected. Source can be star connected as well as delta connected, whatever you feel, whatever the I mean your supply. So but if you use three loads which are connected in as delta as it is shown, then we need to find out what is the relation between your line current and line voltage, line current and phase current, line voltage and phase voltage. So you can see that this here, this is your phase voltage, your EA equal to EB equal to EC, magnitude phase equal to your V phase, right? And what is your, if you take these two terminal, across these two terminal, what is your phase voltage? This is what is your voltage across these two line? It is same as EC, that means your V phase. Between these two, this is also same as EB, so phase voltage equal to line voltage. Then between these two, that is also equal to EA, which is same as phase voltage. So when you have a delta connected system, then your phase voltage is equal to your line voltage. So V line is equal to V phase for three phase delta connected system.
Sir, we are discussing all the parameters with respect to the generator now only, not the final output impedances.
Now
We're only
generator
considering.
as well as a balanced load, because if whenever we find out, we are finding out power, then we should be needing your load, na? Then what is the phase angle, that also we are taking care of the power consumption. Then we have a delta connected supply and we have the delta connected balanced load. So for that, whatever we are getting, we are writing down different parameters. What is the relation between line voltage and phase voltage? Because here also you see your phase voltage is equal to line voltage from the load point of view, isn't it? Whenever we are taking the balanced load. Okay, clear? Is it, it is clear?
Yes, sir. Yes, sir.
Okay, now we should take this load is drawing line current, because we are taking the balanced three phase load which is delta connected, will it will draw the same line current, otherwise this line current will change. Okay, so now you come here at this point. If we take the phase current, if we are interested to find out the phase current like this is what IL and plus I phase is, sum of these two is same as your I phase, isn't it? So we can write, it's disturbing me a lot actually. Your IL is equal to, if this is for phase A, we can write it as I phase, although they are same, but still let me write for the sake of understanding. If this is for phase C, then IL is equal to IC minus IA. So if we now draw the phasor diagram, Then if we use the same, this is your V phase and this is your I phase. Say this is I phase, V phase A, I phase A. This is phi. This is your V phase B and same load. So this is phi I phase B, like this. This is phi I phase C. So what is your line current? Line current is equal to IL for here is equal to I phase C minus I phase A. So what is your I phase A? This is your I phase A. So minus of that means it is somewhere here. What is the angle between I phase C and I phase A? These are 120-degree apart, means if you take minus of I phase A, the angle between them is equal to 60-degree. So if you again take the phasor sum of these two, you'll be getting, it is I phase into root 3. So you will get here just the contrary to your what should I say, contrary of the star connection, where line voltage is equal to root 3 into phase voltage. Here for the delta connected system, it is line voltage is same as phase voltage, but line current is root 3 times that of phase current. Okay. And you check here, if we go for the unbalanced load for this, your phase voltage will be same from the supply point of view, but if you take unbalanced load here, delta connection, then there will be a circulating current between this, which will balance your uh, uh, the difference in the line current, which is actually due to the unbalanced load. So that will be taken care of by the phase current, which will circulate like this, and fourth wire requirement is not needed because there is no neutral point here like the star connection. So these things will discuss again when we'll take for the unbalanced loading, but for the balanced case it is like this. And what is the power consumption? It is same as 3 into V phase into I phase. So 3 into cos phi. Now 3 into VL into, in phase of I phase, you can write IL by root 3 into cos phi. So net power consumption is same as before. It is root 3 into VL IL cos phi. Okay. Okay, so with this we conclude today's discussion. In the next class, we'll go for problem, and then based on this relation, how we can solve it with balanced load. The phasor diagram drawing again we'll do it for the sake of clarity, and then we go for the power. How can we use the wattmeters to measure the total power consumption, like 2 wattmeter method? You have gone through now in your laboratory classes what is the 2 wattmeter method, how using 2 wattmeter we measure the three phase power. Was it discussed? Three phase power, I mean your power consumption for the three phase load, one experiment is devoted na for that. So maybe there it was discussed, but anyway I'll show how we are getting, how we are using it. Using 2 wattmeter, we can calculate the three phase load, power consumption in a three phase load. Okay. Okay, so we conclude our discussion today. I'll do one thing, I'll just put the utility of three phase supply. What are the advantages of three phase supply?